Hello class. Today we're going to learn about why all roads lead to Mole City. So welcome to Mole City. Apparently it's the sandbag capital of the world according to this photo if you read very closely. But so far we've been doing all of these various conversions, and now today we're going to learn how they all relate and how they all go through the mole. So what we have learned thus far, so in section 10.1 of your text, we learned how to convert from molecules to moles and moles to molecules. Okay, we learned how to convert from molecules to moles and moles to molecules. So let's just look at molecules to mole really quickly. So this is review. So I'm going to go through this rather quickly. So here is a sample problem. If you have 7.36 times 10 to the 22nd molecules of barium sulfate, how many moles of barium sulfate do you have? So the procedure has been that we write down what we're given, 7.36 times 10 to the 22nd molecules of barium sulfate. We then go ahead and make our little grid. We then black out this bottom spot. We won't be using that. And now we go ahead and we have to find out what the relationship is between moles and molecules, and of course that is Avogadro's number. So what I've done here is I know that I need to get rid of molecules of BaSO4. So now I need to get rid of this, and so I accomplished that by putting molecules of BaSO4 down there. And so it turns out that 1 mole of BaSO4 equals 6.02 times 10 to the 23rd molecules of BaSO4. Okay? So again, I'm simply dividing the number that I was given by Avogadro's number in this case. And so if we go ahead and look, those units cancel, and if I was to now look at what's left, moles of BaSO4, so if I do that division, I get 0.122 moles of BaSO4. 0.122 moles of BaSO4. So it looks like molecules divided by Avogadro's number equals moles. Now, we can do the opposite problem, which is right here, moles to molecules. Here's a problem. If you have 0.632 moles of barium sulfate, we'll keep this with barium sulfate so we don't have to go back, and so we can kind of keep the same relationship. How many molecules of barium sulfate do you have? Again, you write down what's given, 0.632 moles of BaSO4. We go ahead and make our little grid. We can then cross this out. Okay. And we will go ahead and add in the conversion factor. And now what has happened is we've now trying to get rid of moles of BaSO4. We put moles of BaSO4 down here, and again those will cancel, and what's left behind is molecules of BaSO4. Okay. So you see the moles cancel, and we have 0.632 times 6.02 times 10 to the 23rd, and that will equal 3.80 times 10 to the 23rd molecules of BaSO4 when you punch that into your calculator. So again, moles times Avogadro's number will equal the molecule. So if you have moles, you just multiply by Avogadro's number. If you have molecules, you divide by Avogadro's number. So this was a homework that we did a few days ago, and most of you seem to have a handle on it. So that's the first thing we've learned. What else have we learned? The other thing we learned in section 10.1 was just how to calculate the molar mass of a compound. Very simple. We learned how to do that. Okay? For instance, let's say, what is the molar mass of CuHAsO3? Most of you are pretty good at putting this together. I have a copper. I have one hydrogen. I have one arsenic in this case. This is a bit of a peculiar molecule. But then I have 3 oxygens. So you multiply those by 16. You add all those numbers up, and you get 187.4 grams per mole. Again, remember the units. So you get 187.4 grams per mole. Now, the only reason we learned how to do molar masses is so that we can then do what we studied yesterday, which is converting between grams and moles. So let's take a look at that. So in section 10.2 of your textbook, if you should be reading that. You'll learn that how to convert from grams to moles and moles to grams. So that was the homework that I handed out yesterday, and the homework will be due on your lab day. But it's just simply going back and forth between grams to moles to grams. So I have also a few samples of that, or one sample of each. So let's talk about going from grams to moles. So again, this should be something that you don't necessarily have to take notes on, but that you can look at, go back, and appreciate. And again, you've basically have a homework where you're doing similar problems like this. So this question says, if you have 12.212 grams of CuHAsO3, how many moles do you have? So you start with what's given. We go ahead and make our little box. One of the good things that you should always do with these problems is just go ahead and calculate the molar mass. So whenever you see the word grams, it's not a bad idea. You can put what's given, but then you should also go ahead and do the molar mass. Now, we already calculated that molar mass, but we'll just show it here. It was 187.4 grams per mole. That was on the previous slide. So now we know that that's our conversion factor. So to go between grams to moles, we need to use the molar mass. To go from molecules to moles and back and forth, we need an Avogadro's number. So I'm going to go ahead and put these in. Now, if you notice what I've done is I've tried to get grams here up top. So now I know I have to put the grams part down here to get rid of those two, which means the 1 mole of CuHAsO3 has to go on top. So remember how to do that. So when you do that, you can cancel those units. And it looks to me that if you take 12.212 and divide it by 187.4, you'll end up with moles of CuHAsO3. And this is the number I got. This is my calculator number. Should say 0.065165421 moles of CuHAsO3. However, that's an improper. This is an improper use of the numbers because we need to calculate significant figures. So if you do significant figures, it looks like we have 5 significant figures in the 12.212. So we have 5 sig figs here, but 187.4 is 4. So our answer should have 4 significant figures. So let's go ahead and do that. And here is your answer with 4 significant figures. 0.06517 moles of CuHAsO3. Or probably a better way to express that is 6.517 times 10 to the minus 2 moles of CuHAsO3 would be our answer. So it appears that grams divided by molar mass equals moles. Okay, grams divided by molar mass equals moles. Let's go do the other one, which is moles to grams. Okay, so in moles to grams, here's another sample problem. If you have 1.54 moles of CuHAsO3, how many grams do you have? So again, let's write what's given to you, 1.54 moles of CuHAsO3. Let's go ahead and make our little boxes again. Once again, whenever you do your work, I'll just do this again for completeness sake, but you could put 187.4 grams per mole on the bottom. You do that molar mass calculation. Again, when you see the word grams, you should immediately look for the chemical in question and just get its molar mass. Do that work off to the side. So there you go. Now, what I've done here is, again, I know that I need to get rid of moles and I have to end up with grams. So again, moles are here, so I know that those will end up canceling, and I put grams on top, which is what I want at the end. My answer at the end should be in grams. So let's take a look at this. Again, those cancel. So it looks like 1.54 times 187.4 will give me the grams of CuHSO3. Okay? And so I get a number of 288.596. I'm looking at my sig figs. I see 3 here. I see 4 here. This to me looks like it should be probably 289. Should round up because it's 288.59. Let's see if that's the case. Yep, 289 grams CuHASO3. Again, only 3 significant figures because of the 1.54 number above. So it would appear to me that moles times molar mass equals grams. So at this point, we've basically shown you 4 samples: molecules to moles, moles to molecules, grams to moles, moles to grams. So these are all sort of practice. These are all review for you. And what we're going to do for the rest of this lecture is basically put it all together in kind of one fell swoop so you can kind of see it pictorially and then see how you can solve more complex problems. Now, before we get on to these more complex problems, which are known as mixed mole problems, we do have one delayed objective, and we go back and forth on whether we should teach this or not. This year, Miss Page and I have decided to teach it along with gases. So this is also in section 10.2 of your textbook, and it's to learn how to convert between moles and volume. We just decided to omit that for the time being. However, you will learn this when we derive, so we'll actually derive the ideal gas law in chapter 14.3. This is our chapter on gases. But even though it is delayed, just to let you know, really all you need to know is how to multiply or divide by 22.4. There's some other caveats, which I won't go into too much, but for the most part, when you look at your mole city chart that you picked up today, you will see that there's also a way to go to quote-unquote the gas station, and you can see you're either multiplying or dividing by 22.4. So there's probably a number of you, just by reading the textbook, you'll understand that when we have reactions that are in the gaseous form, you can go back and forth with liters of gas as well. So now what I'd like you to do is just take out your mole city map that hopefully you picked up today. They're up front. You should have picked one up. If not, please quietly go pick one up. But this is the All Roads Go Through Mole City map. And let's just look at this for a little bit. And there's a little bit missing from here, so maybe I can put it in. First of all, here's Mole City. It's rather large. As you can see, it looks like a burgeoning metropolis, if you will. And we have 3 places you can go. There's Grahamville, there's Molecule Town, and we've actually been practicing going back and forth to those 2 places. And then there's the gas station, which again we're going to delay until 14.3. Now the other place that you can go is, let's see if we can see it here. I'll kind of draw a road going back this way, so it's a road that only leads out of Molecule Town, and this can actually go to Adamsburg, or the place where we can calculate atoms. So we'll have a problem at the end, so you can also go from molecule town to atoms. But the only way you can go from Atomsburg to Mole City or to Grahamville is to go through molecule town. So keep that in mind. So now I'm going to go ahead and erase all the strokes here. Now let's look at this again. If you think about the first homework that we did, which was after the molar masses, we learned how to do that, but we were basically going back and forth between molecules to moles and moles to molecule. So if you think about that, what we were doing was we were practicing going this way and we were practicing going this way. So you had 5 problems where you went this way, and then you had 5 problems where you went this way. So in effect, what we were doing was practicing the movement between molecule town and mole city, or if you will, how to convert between molecules and moles and go back and forth. And then the homework that we assigned yesterday and that I just gave some samples of, we learned how to go back and forth between these 2 places. Okay? How to go back and forth between these 2 places, between Grahamville and Mole City. And what we learned is that if you want to go back and forth between molecule town and Mole City, or from moles to molecules, it all has to do with Avogadro's number. Okay, so I'll erase the strokes again. It all has to do with Avogadro's number, multiplying or dividing by Avogadro's number. Now going between Grahamville and Mole City, and I want to point out that this is the one that you're going to be doing the most, going between grams and moles, is that you have a different number you use every time. It's the molar mass. And so the molar mass changes. So unlike going to molecules and moles, between those two, basically you're always using the same number, Avogadro's number, but between Mole City and Grahamville, you're always having to calculate a molar mass, so keep that in mind. And last but not least, we didn't talk about this, but here's the gas station, and again, we'll cover that later on, but as you see, it's just another number, 22.4 liters. The 22.4 liters only qualifies at certain standard temperature and pressure, which we'll talk more about later. So those are basically the 3 things that we've the 2 things that we learned, the other thing that we will learn. But we've been practicing essentially one-way trips back and forth. So now what we're going to learn for the rest of the day, and there's just a couple more slides, but they're problems we'll work on for a little bit, is like basically what if we want to go from Grahamville over to Molecule Town, or Molecule Town to Grahamville? Is that essentially eventually we'll learn how to go from Grahamville to the gas station, maybe back and forth between these 2. But all of these arrows that I've drawn are incorrect. We can't go those routes. And that's the point of this Mole City map, is that all the roads must go through Mole City. Mole City is the hub where everything happens. And what does this mean for you and what it means for chemists? It means that generally speaking, when we're doing stuff, we just have to convert stuff to moles. We got to get it to moles because it's at moles where we can compare molecules on an even basis. When we get to chapter 12, which is just after this, we're going to talk about stoichiometry. We're going to put that into practice and see how these things are really like recipes, and we have to compare moles to moles in order to compare molecules to molecules. We can't compare grams to grams, that type of thing. So again, all roads must go through Mole City. So what that means to me is that if I wanted to, for instance, go from Grahamville to Molecule Town, it looks to me like I have to first divide by the molar mass of my compound. That would give me moles, but then I would just go on and multiply by 6.023. Conversely, I could go from the number of molecules given, divide by 6.023, and then multiply by the molar mass to get to Grahamville. Okay? So let's do a few sample problems. So here's our first sample mixed mole problem. It's going from molecules to grams. So let's just see what the problem says. So here is the problem. What I'd like to have you do right now is go ahead and take out your whiteboards and write this problem down and then see if you can work it. So I'll have the teacher, the substitute, pause the recording at this point and have you work for 4 or 5 minutes and see if you can solve this problem, and then I will show the answer. Okay, so now I hope you've have an answer that maybe you've worked with a partner and you have an idea of how to solve this problem. And now I'm going to go ahead and solve this problem for you. So again, it says if you have 3.45 times 10 to the 10 to the 25th, excuse me, molecules of NH3 or ammonia, how many grams do you have? So again, the and get its molar mass. I know that the nitrogen's 14.0, hydrogen, there's 3 of them, 1.0, there's 17 grams per mole. And then I would circle that that bugger and just set it off to the side. I've done a calculation. I would double check that calculation, especially for more complicated molecules. There's my molar mass. Then next, I'm going to go ahead, what have they given me? 3.45 times 10 to the 25th molecules of ammonia. Let's go ahead. Now notice that when I talked about molecity, I said there's two things you have to go. We have to go from molecules to moles, and then moles to grams, or molecule town to mole city to Gramville. So now I've left room for two separate conversion factors. That's what this T is right here. So the first thing I know is that I'm going to have to get rid of molecules of NH3. And so I'm going to put Avogadro's number on the bottom again. That's dividing by Avogadro's number, and that means there's 1 mole of NH3 per 6.02 times 10 to the 23rd molecules of NH3. And now I'm going to cancel units. So if I was to do this conversion, this is basically what we've done before. This is our one-way trip to mole city, and we're just taking the molecules given to us and we're dividing by Avogadro's number. But we're not done. We do need to get rid of moles of NH3. We can do that. We'll put moles of NH3 in the bottom, and then 17 grams, 17.0 grams of ammonia on the top. So again, now we have the molar mass, and to get rid of these moles and be left with grams. So if you look at this, we've put two of these problems together. One we've divided by Avogadro's number to get to mole city, and then out of mole city you multiply by the molar mass to get to grams. So now it looks like if you take 3.45 times 10 to the 25th, multiply it by 17, and then divide that all by Avogadro's number, you'll have the answer to this problem. When I do this, I get an answer of 974.252 grams of NH3. I look and I see that I should have 3 significant figures because all of my answers have 3 significant digits, so that I've basically rounded that down to 974 grams of ammonia. And that would be the answer. So double check your answer, see if you have that set up. This would be a pretty standard mixed mole problem. Again, going from molecules to grams. Does this answer make sense? Yes, 3.45 times 10 to the 25th is bigger than 6.02 times 10 to the 23rd by 2 orders of magnitude to the 25th versus the 23rd, and we're multiplying that by 17, so this number isn't out of reality. If we had a number that was 3.45 times 10 to the 22nd that was smaller than Avogadro's number, then I would expect an amount of grams that was less than 17, the molar mass of ammonia. This is our last problem, and I put a little twist to it, but it's going from grams all the way to molecules/atoms. So this is a sample mixed mole problem. Again, why don't you erase your whiteboard and go ahead and write this problem down. If you have 66.23 grams of carbon dioxide, CO2, how many oxygen atoms do you have? Notice I'm not asking for molecules of CO2, I'm asking for oxygen atoms. But remember, I said to get to Adamsburg or get to atoms, you have to go through molecules. So think about how you would do that problem. And again, pause the video. The video can be paused, and you can work on this for 5 minutes with a partner or a small group. Okay, so let's see how you did. I'll go ahead and work this problem step by step. probably take me a few minutes, and then we'll go ahead, and there's some similar mixed mole problems that will be due later on if you look on the schedule over to your, I believe it would be your left. Okay. So the first thing is I see CO2, so I'm going to go ahead and just go ahead and go ahead and get the molar mass. I do that. That's 44.0 grams per mole. The molar mass of carbon dioxide is actually one of those that I like to memorize. I have that basically memorized. I know it's 44. Again, circle it, tuck it away. When you do work on an exam, get that off to the side. Let me see that. Generally speaking, on these complicated problems, they might be worth 4 or 5 points. I'll probably give you a point just for doing the molar mass right. So there's some partial credit there. So now we have to go and set up our problem. And so what I've done is I started out by putting, again, like every other problem, what's given? 66.23. I'm going to go ahead, just like before, and make this table, if you will. And what am I putting on the bottom? I know I have to get rid of grams, so I know right away it looks like if I have to divide by the molar mass. So that 44 grams, where does that come from? A lot of times kids just, where does that come from? They forget. But, oops. Well, let's not do that. Comes from right there, 44 grams. And again, I know because I'm trying to get rid of these guys here. I'm trying to get rid of grams of CO2. Okay. And so I know that it's 1 mole of CO2 for 44 grams of CO2. So all of a sudden my units cancel there. And it looks like if I take 66.23 and divide by 44, I would now have moles of CO2. I don't have to do that calculation separate, but I know if I did, that would be the moles of carbon dioxide. So that means I'm in Mole City. So I've basically traveled from Granville to Mole City. I'm sitting there, but I don't want to go to Mole City. I actually want to go to Adamsburg, but I told you got to go through molecule 10. So molecules, Avogadro's number should come to mind. So let's look about that. I do know that I need to get rid of those moles, because that's not where I'm going, so I put moles on the bottom again so that I can eventually, wipe. I should switch to this so that eventually I can get rid of those. So I know that I'll need to do that. So let's just go ahead and try that. And so I've put Avogadro's number now on top. And so let's see, it looks to me like I can cancel these units. And so now it looks like if I take Avogadro's number, I multiply it by 66.23 and divide by 44, I would now have molecules of CO2. So if I'd asked for how many molecules of CO2, you could stop right here and you would actually be done. You would be done with this problem. But I didn't ask for molecules of CO2. I asked for atoms. So what that means is that you need to find some other conversion factor where atoms are on top, atoms of oxygen, and molecules, CO2 is on the bottom. And let's go ahead and look at that real quick. So this is what I did. First of all, I said, I need another conversion factor, so I need another box. So I made another box, table if you will. And then I just look at the molecule itself. Just look at the molecule, and what you'll see is there's 2 atoms of oxygen for every molecule of CO2. It's right there, because it's CO2. So I just write out this simple conversion factor, 2 atoms of oxygen over 1 molecule of CO2. My molecules of CO2 cancel. What does this mean? To go from molecules to atoms, I simply have to multiply by 2. Why? Because there's 2 oxygen atoms in a molecule of carbon dioxide. So now 66.23 times 6.02 times 10 to the 23 times 2, divided that whole thing by 44. I got an answer of 1.8123 times 10 to the 24th oxygen atoms. And it looks to me like I need to probably do 3 significant digits, because I see 4 in the first one, but I see 3 for 44.0, 6.02. Don't worry so much about the 2 atoms of oxygen in 1. And so I'm going to write this as 1.81 times 10 to the 24th oxygen atoms. So there you go. There's a mixed mole problem. So I have a homework for you. Some of the problems are a little bit more complicated. They ask the questions in a little bit of a round way. The first two problems, however, are very similar to what we just did. The other ones require you to think maybe a little bit harder. So I hope you understand all this. And again, obviously, when I get back, we'll spend more time talking about how to do these mixed mole problems. Thank you.